Welcome guys and girls to the system design course. If you are someone who is preparing for an upcoming system design interview, or you want to know how different system design concepts are put together to create modern applications, this course is for you. This course will teach you the basics and set you up to learn more intermediate and advanced concepts. We are going to cover monolith versus microservices, how microservices are implemented on AWS. Then we are going to learn about load balancers and what is the difference between application load balancer and network load balancer. Then we are going to learn about API and API gateway. What is the difference between load balancer and API gateway, and when should you use what? Then we are going to learn about vertical versus horizontal scaling, and how does scaling in virtual machines, serverless, and containers differ from each other. Then we are going to learn about some real-world scaling interview tips. And finally, we are going to put all these concepts to work and design a 3-tier architecture. For those of you who are new to the channel, my name is Raj. I'm a senior solutions architect at AWS. Previously, I was a distinguished cloud architect at Verizon. I'm also a published Udemy and Pluralsight author, public speaker, and author of multiple AWS blogs. If you are new to this channel, please make sure to subscribe. I upload videos on system design and container, DevOps, serverless, interview preparations every week. All right, let's get started. Before we learn about microservices, let's take a look at the elephant in the room, the monolith. Monolith is a single-tiered software application in which the user interface and data access code are combined into a single program from a single platform. Some examples of monolith are a single Java jar file which handles business logic for different areas of your project, or a COBOL program handling different functionalities. Monolith is not really the bad guy, because at first monolith is simple, especially for small projects. Since everything is contained in a single code base, there is no over-engineering. It is also resource efficient at small scale. But as your projects begins to grow, modularity is hard to enforce. Scaling is a challenge, so this is the important part to understand, especially during the interviews, so we'll dive deep into the scaling part. Monolith has all or nothing deployment because everything is contained in a single code base. Either the whole jar file or the whole COBOL file goes in, or everything gets backed out. Monolith leads to long release cycles because over the time that single code base gets bigger, so even if you are not touching some functionality, you still need to test it out to make sure they are not impacted because they are part of the same code. Hence, the businesses are slow to react to customer demand. Now let's talk about a very common misconception. Can you use API with monolith? Absolutely. APIs has nothing to do with monolith or microservices. Your monolith can be fronted by an API gateway or a load balancer. And when different URL or paths hit this API gateway/load balancer, they could forward all these calls to the same monolith. And this monolith will have an entry function or entry paragraph which will check the URL or path and invoke different functions within the monolith and executes the logic accordingly. Now let's talk about the scaling of monolith. Let's say our monolith is running on virtual machine. And since you are running this huge program as one executable, you need a sizable EC2 instance. In this example, this EC2 is M5.12x large, and we have these 3 different traffic patterns coming in for store/get, store/post, and store/delete. So as the name suggests, you can imagine store/get gets some information about some product, store/post posts information about a product or a customer or a purchase, and store/delete deletes information from the database. So let's say the traffic for store/get increases. So the CPU, as you can see, increased to a threshold limit. And if you have auto scaling group set for this virtual machine and the threshold for that auto scaling configuration exceeded, which it is in this case, instead of scaling just the CPU needed for the store/get component, you have to scale the entire monolith, right? Because you cannot really pick apart different components to run on different EC2s with the monolith approach. So now we have two M5.12x large EC2s running, and the CPU utilization for both of those went down. So even though you are using part of the CPU, you still pay full price for these Amazon EC2s, since you have to assign a sizable virtual machine for monolith, so you end up paying a lot more. So how would it look like with a microservice? So with a microservice, all the three components, store/get, store/post, and store/delete, have different code bases. And on the back end, you can see they are running on different virtual machines. And depending on the type of the API, you can control the memory and CPU of the EC2. In this case, store/get backend is running in a T3.large, store/post backend is running in T3.medium, and store/delete backend is running on T3.micro. Now you might say, Raj, this is not a right microservice because each microservice should have their own different database. Ideally, yes, but in real world scenario, it is not possible sometimes to break the big database into multiple small databases. So we are going to talk about the characteristics of microservices, but remember that it is not all or nothing approach. In real world enterprise projects, you fulfill some characteristics of microservice that makes your business agile and makes your life easier, but it doesn't need to check all the boxes. So going back to our previous example where our code base is separate and it is using the same database, now let's say store/get traffic increases. Instead of scaling up all the three different EC2s, only the virtual machine that's running store/get backend needs to scale. If you are using the single database for multiple microservices, you do need to keep in mind as the microservices scale, the database should be able to handle the increased connections. Generally, there are a lot of techniques to optimize the reading from the database, such as you can use read replica, caching, etc. Another advantage of using microservices is, since all these backends are independent of each other and could be maintained by different teams, these microservices can be written in different programming languages. So the store/get could be written in Python, store/post backend could be written in Node.js, and store/delete backend could be written in Go. There is a fancy name for this feature. We call it polyglot. So what are the characteristics of microservice architectures? The core property is each microservice is independent of each other. So each can scale irrespective of each other, as we saw. Since they are separate, you can apply different governance and security features, and you can deploy each of them independently. This makes your DevOps much faster and simpler because it is no longer an all or nothing approach. You can just deploy store/post backend without deploying store/delete or store/get. You can test these microservices independent of each other, and they should have different functionalities. And as I mentioned before, the important thing is it is not required to follow every characteristic. The main characteristic is independent scaling and independent functionality. However, like I mentioned, sometimes you will see the same database being used for more than one microservices. Now that we understood about monolith versus microservices, let's talk about how can you implement microservices in AWS. So we have one service which is answer to everything and that is Amazon EC2. There is a misconception that you cannot run microservices on Amazon EC2, which is not correct. So as we saw before, each microservice can be running in their own Amazon EC2. Each of those Amazon EC2 could be part of different auto-scaling groups with different scaling criteria. You can select appropriate Amazon EC2 family based on the nature of the microservice. So if some microservice is memory intensive, you can select a higher memory EC2 and you can scale based on memory instead of CPU. You can use Elastic Load Balancer or Amazon API Gateway to host those microservices. Beyond EC2, for modern application development, we can look at the serverless alternative, which is AWS Lambda, where each microservice's backend will be implemented in separate Lambda functions. Remember that Lambda scales automatically, so there is no auto-scaling group in this case. And Lambda could also be fronted by Elastic Load Balancer or Amazon API Gateway. Now, another popular choice is using containers. You can containerize your application and run within Amazon Elastic Kubernetes Service or EKS or Amazon Elastic Container Service or ECS. And in this case as well, you can front it by using Elastic Load Balancer or Amazon API Gateway. So let's zoom in into the Kubernetes part because Kubernetes is super popular right now and this might come up in your interviews. So for Kubernetes, each microservice will be fronted by different services, so service A, service B, and service C, and the code for each microservice will be running in a container, and this container will run in a pod. And all these will be fronted by a single ingress, which will be an application load balancer. Now, this is a deeper topic which is beyond the scope of this course. If interested, check out my container and Kubernetes course in Udemy. Since each microservice is independent of each other and can even be coded in different programming languages, you can mix and match all these AWS services. So for example, store/get can run on a pod where your backend of the microservice is Dockerized into a container. Store/post can be hosted on Amazon EC2, and store/delete can run on AWS Lambda. So which one should you choose? So the answer is it depends. Based on the requirement of the project, you have to choose different backend for the microservices. We will go over different scenarios down the line in multiple lectures. So at the end of this course, you should be able to pick the right tool for the right job. One general tip is for interview, go with the service that you are most comfortable with if you have a choice to pick one. Alright guys and girls, that's the lecture. I will see you in the next lecture. Welcome guys and girls to this lecture. In this lecture, we are going to learn about load balancer. So let's say your application, which is written in Java, so the jar file is running on a virtual machine such as Amazon EC2. So how will you, the user, access or invoke this application? So one way could be each Amazon EC2 will have a IP address, so you can directly invoke this IP address to invoke your application. But there are caveats to it. What if this Amazon EC2 goes down and another new Amazon EC2 comes up in its place with another new IP address? How will you discover that new IP address? Also, what if this application scales and now instead of one Amazon EC2, you have 3 Amazon EC2s? What if it scales further up and more EC2s keep getting added? How will you discover those EC2s as well as invoke the application and ensure that the traffic is balanced between all these EC2s? That's where load balancer comes into play. Elastic load balancing automatically distributes incoming application traffic across multiple targets, such as Amazon EC2 instances, containers, IP addresses, etc. And each elastic load balancer will have a unique DNS name so that your user can invoke this application using this DNS URL. And if the traffic goes up and your backend needs to scale up, and let's say it adds another EC2, the load balancer will automatically discover this new EC2 instance and start distributing traffic to it. It also tracks the health of all these EC2 instances. So even if one EC2 goes down, the load balancer is smart enough to detect that one EC2 is down, and it will start distributing traffic to the rest of the healthy backend targets. Similarly, with Kubernetes pods, load balancer can distribute traffic across multiple pods, and in this case, the load balancer will act as ingress or service. Similarly, even if your application is running in Lambda, load balancer can distribute traffic to those as well. Now, what if your application should be exposed with a website that you already have, such as www.store.com? How do you solve that? Because Elastic Load Balancer gives you the DNS. Well, you can use Elastic Load Balancer with a DNS service such as Amazon Route 53. So anytime user invokes www.store.com, the traffic first goes to Amazon Route 53, and from Route 53, using an alias or an A record, those traffic can be forwarded to this load balancer. So what are some of the properties of load balancer? We already learned that load balancer automatically distributes incoming traffic across multiple targets. It monitors the health of targets. Load balancer also integrates with SSL, and as the name suggests, elastic load balancer means as the traffic goes up, the load balancer will also scale up. And this part is managed by AWS. You do not need to do anything for that. Load balancer is also highly available out of the box. Under the hood, the load balancer is running in multiple availability zones. So moving on to types of load balancer, there are two different types of load balancer: application load balancer and network load balancer. So what is application load balancer? So let's say your website is www.store.com and you want to invoke different backend for different URL. So let's say www.store.com/get should go to particular EC2s/post should go to different EC2s, and similarly /delete should go to different EC2s. With application load balancer, using the path, you can distribute traffic to multiple target groups. What is the advantage of it? So in this way, for each URL, the separate target groups can scale independently without impacting the other operations. So some of the properties of application load balancer are: application load balancer operates on OSI layer 7. It routes traffic based on URL path. And going a little deeper on this one, for different URL, the backend doesn't need to be same. So for example, www.store.com/get could be sent to a target group comprised of Amazon EC2s, whereas store.com/post can send the traffic to Kubernetes pods. Similarly, store.com/delete can send the traffic to AWS Lambda. And all these can be done from a single application load balancer. Going back to the properties, application load balancer can validate and terminate SSL. So for AWS, application load balancer can integrate with SEM or Amazon Certificate Manager and validate the certificates. Now moving on to network load balancer. Network load balancer operates on OSI layer 4, which means that it can route traffic based on protocol and the port of incoming traffic, such as TLS with port 443, which translates to HTTPS traffic, or protocol TCP with port 80, which translates to HTTP traffic, and a couple of other protocols, such as UDP, TCP_UDP, along with various number of ports. So note that network load balancer cannot distribute traffic to different backend based on the URL, because URL path is application layer property. With network load balancer, default behavior is SSL pass-through. What that means is a network load balancer is not going to validate the certificates. It is just going to pass them through to the backend server, and the backend server needs to validate the SSL certificates. Note that previously there was no option to terminate SSL certs in network load balancer, but with a new feature now that's possible. So by default it is not terminated, but if you go and turn it on and configure some fields, point to the appropriate certificates, then you can terminate SSL certs in network load balancer right now. So this is a related blog from AWS that goes over step by step what to do. So if you want to know more, Google that and study this up. Keep this in mind that now network load balancer, you can do either SSL pass-through or you can terminate SSL. So the question of the hour is, should you use ALB, application load balancer, or NLB, network load balancer? Well, it comes down to a couple of factors. Network load balancer handles spiky traffic better. If you need an IP address instead of a DNS URL, the network load balancer exposes a static IP address. You can have an IP address with application load balancer, but you need to use global accelerator. And sometimes your decision will be influenced by the choices you have, such as if you are using API gateway REST API and you want to do private integration with your backend Kubernetes cluster, ECS cluster, or EC2, REST API will expose a network load balancer with private link. It is not going to expose the application load balancer. So in those cases, you have to use network load balancer. Network load balancer supports EC2 instance and IP address as backend target group. Note that it does not support Lambda. Application load balancer supports EC2, IP address, and Lambda. And note that I haven't mentioned Kubernetes for either NLB or ALB backend support. These are just out-of-the-box integration. Since to integrate with Kubernetes, you need to install Ingress and do a couple of steps. That's why I did not mention this here. But both network load balancer and application load balancer supports Kubernetes pods as the backend. However, as we learned, application load balancer can forward to different Kubernetes pods based on the URL, whereas network load balancer can only send traffic based on the protocol and the port. So these are the few things that you should keep in your mind when deciding ALB or NLB. Alright guys and girls, that's it for this lecture. I'll see you in the next one. Now the question of the hour. What is API and why do we need them? As per Wikipedia definition, an application program interface or API is a connection between computers or between computer programs. It is a type of software interface, blah 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 blah. Doesn't make much sense. Let's try to understand API with a real world example. Let's say you go to a restaurant and you have a menu from which you can order food from. And we have a kitchen with the chef inside the kitchen. But you do not go directly to the chef to give your order. You have a waiter who takes your order from this predefined set of food items from the menu, takes the order to the kitchen, and then brings the requested food to your table. So in this case, the waiter is acting as an interface between you and the kitchen. So the waiter is an API in this case. So now if we go back to our IT world, Instead of kitchen, the backend system could be a bank, airline booking system, Tinder, Uber, Amazon, etc. And all those applications will be running in some sort of compute layer, let's say Amazon EC2, and you interact with those systems using API with some predefined input fields. But why do you need API? Like in previous example, why can't you just go to the chef and order directly? Similarly, why can't you call the application program directly without using an API? In real-world business, there are multiple users who will be accessing that application. In some cases, millions. So beyond just invoking the program with some input parameter and getting output, there are a lot of other factors such as traffic management, load balancing, specific input-output needs, authentication, authorization, and many more. If you want to code all these things in your application program, there are a lot of overhead because all these interfacing parameters have nothing to do with the business logic that's running your application. So coding all this into your program makes it very difficult to modify, test, and deploy your code. And inversely, there are a lot of open interfacing standards that you need to implement, and implementing all this with your application code makes it very cumbersome and painful. That's why you need a separate layer, and you move all these interfacing parameters into this layer. We call this layer or orchestrator as API Gateway. API Gateway hosts all your API, takes care of throttling, authentication, managing backend, and much more. An AWS implementation of API Gateway is Amazon API Gateway. As you can see, this is very similar to load balancer. So what are the differences? Join me in the next lecture to understand the exact differences between load balancer and API Gateway and when should you use what. All right, the face-off, the showdown between ALB and API Gateway. So in this video, I'm going to briefly touch on Amazon Application Load Balancer and API Gateway, and then we are going to dive deep on the differences and when should you apply what. All right, let's get started. So what is Application Load Balancer? It automatically distributes incoming traffic across multiple backend targets. ALB is a layer 7 load balancer, so it works on the application layer. The underlying infrastructure is managed by AWS. The underlying infrastructure is highly available and elastic, so if the traffic goes up, your load balancer should scale up as well to accommodate the increased rate of traffic. So some typical ALB integration would be your website sending requests to the application load balancer, and you will configure different route in the load balancer. So if the incoming path has /browse or /insert, maybe they will forward to target groups with AWS Lambda. If the path has /delete, then they're going to forward to AWS EC2. Okay, moving on to API Gateway. API Gateway is fully managed and serverless API service from AWS. This also automatically scales up and down with traffic. And also for API Gateway, infrastructure is managed by AWS. It is highly available and it is also elastic. So a typical pattern of API Gateway integration will be your website calling different APIs. All those APIs will be hosted in Amazon API Gateway. And for different HTTP methods such as /get, /post, /delete, it can go to different Lambda or AWS EC2 endpoints. So which brings us to the topic of today's discussion is what is difference between ALB and API Gateway? All right, so let's take a look. So for API Gateway, you can implement rate limiting, bursting for APIs. If you want to control like, hey, this client can only call these APIs 10,000 times a month with this much burst limit, you can do all that for API Gateway. ALB doesn't offer any such feature. So even though the next point is not a difference, but I wanted to mention it because it's the important one. Both API Gateway and Application Load Balancer integrate with AWS Web Application Firewall for protection out of the box. You just have to click a button, that's it. API Gateway It is not possible to get a static IP address for endpoint. You will always have the URL. ALB, it is possible to get a static IP address for load balancer endpoint using Global Accelerator. API Gateway only accepts HTTPS traffic. ALB accepts both HTTP and HTTPS traffic. API Gateway, this is a big feature of API Gateway. It is able to do request validation, request response mapping. You use a template called Apache Velocity template, and you could check if some particular fields are present in the input API request, and if, let's say, you are expecting a field called account number in the input API request, and if it is not there, you can reject it straight away from API Gateway. You do not have to go to the backend and code all that stuff. Similarly, for request response mapping, let's say some particular value is coming in a field, and then you want to move it to a different field before you send it to backend. You could do that. For example, let's say a GET API is sending an account number in a field called account_number, but the backend is expecting the field to be ACCTNO. So you could do that. You can move the value from that account_number field to ACCTNO before you call the backend. Not able to do that in application load balancer. So API Gateway able to handle spiky traffic. So both can auto scale up and scale down. That's not a problem. But if the traffic goes up super fast, API Gateway is little faster to respond because the nature of the underlying infrastructure. The default rate is 10,000 RPS rate per second, and it can immediately allocate up to 5,000 burst rate. ALB, if the traffic is super spiky, there could be a little delay. However, you can pre-allocate LCUs. We're going to take a look at the LCUs. This is like the capacity unit for ALB. It's like you can pre-warm underlying EC2s for ALBs, and then even when the traffic spikes, you won't face a delay. However, you have to pay extra for this because you are keeping things pre-warmed. Next, API Gateway able to integrate with Lambda. I'm just showing it for one service. It is able to integrate with Lambda from different region, even different AWS accounts. So if you have your Lambda in a different AWS account, but your API Gateway in another account, your API will be able to integrate with that Lambda. ALB is a regional service. So even within an account, ALB can only talk to services, the backend services, let's say Lambda or EC2, running within that region. You don't be able to go cross region and cross account. So going next, API Gateway, you can able to export, import APIs from cross API platforms using Swagger or OpenAPI Spec 3. So basically, this is very, very popular. Let's say you are running your API today in Apigee, right? Or some other API platform like Kong API, MuleSoft, etc. And you want to test out API Gateway. So you can export those APIs from those platforms using Swagger, and you can import it in API Gateway, and your API will be defined. Very little infrastructure as coding required. Similarly, if you don't want to get locked down in API Gateway, you can export out Swagger from API Gateway and then define it in other API management platforms. ALB, there is no direct method to import, export rules for cross platforms. Like if you have coded a bunch of routing rules in application load balancer, typically you will do that using CloudFormation. So if you want to move to another load balancer from another cloud or another company, you have to code that stuff again. You cannot just import export easily. API Gateway have extensive authentication and authorization, authn/authz integration. So out of the box, it integrates with API Key, IAM, Cognito User Pool, Cognito Identity Pool, and external identity provider. ALB, it integrates with any YDC compliant identity provider such as Cognito, LDAP, etc. But it doesn't have integration with like API Key because API Key is API concept. API gateway able to cache the responses. So for a specific method, if you think it is going to return repetitive value, you can cache it. ALB, you are not able to cache any responses. API gateway, however, the timeout limit for API execution is 30 seconds. And application load balancer timeout limit is 4,000 seconds, so way longer timeout limit. API gateway integrates with almost all AWS services. If you go to API gateway console, click the backend integration, you will see a lot of AWS services in there. ALB integrates with EC2s, Lambdas, and IP addresses as backend. It cannot integrate directly with all different services that API gateway can do. API gateway, there is no health check, like it's not gonna periodically go and check if the backend service is up and running. If you want to implement it, you have to do it yourself. Like you can, let's say you have a Lambda as a backend, you can create a CloudWatch scheduled rule, which is gonna go ping the Lambda and see if the responses are coming as expected. ALB, health check is available. It can ping the backend services and see if it is working okay. That's how it determines whether the target is healthy or not, right? If it is not healthy, it routes to a different target. So API gateway is a serverless service. So what that means, it's pay per use. So if the API gateway is idle, if there are no API traffic at all, then you don't pay anything for API gateway. Unless you enable caching, then you pay for the caching capacity. But let's say you don't have caching enabled, then you don't pay anything for idle API gateway. ALB, think of it like EC2. So to run a application load balancer for you, underlying there is a EC2 running. So you have to pay for a charge even if ALB is idle. So this calculation is a little bit complicated. So I'm just gonna show you the pages and you can take a look at it. Okay, so this is the page for Amazon API Gateway pricing. You can just Google it, it will come up. So API Gateway has a generous free tier. The free tier includes 1 million API calls received for REST APIs, 1 million API calls received for HTTP API, and there's some other stuff. So if you are trying to do a proof of concept, API Gateway will probably cover you in free tier. Beyond that, so HTTP API is the new flavor of API for API Gateway. But if you are able to use HTTP API, always use HTTP API, no need to use REST API. So for HTTP API, the price is cheaper than REST API. You can see first 300 million after the free tier is $1 per million, and after 300 plus million for 90 cents per million. And HTTP APIs are metered in 512 kilobyte increments based on the payload. REST API a little bit more expensive. First 333 million, price is 350, and then next 366,667, price is 280, and then you can see the prices go down as the volume goes up. The caching is only available for REST API, but you can see depending on the amount of caching you allocate, the price changes. But again, if you can use HTTP API, you should always use HTTP API. Okay, now going back to load balancing. So load balancing pricing is a little bit more complex. So there are 3 different load balancers that AWS offers: application load balancer, network load balancer, and classic. So we are talking about the application load balancer. So you could see it has 2 components to it. One is 0.0225 per application load balancer hour or partial hour, and 0.008 per LCU hour. So then it goes into detail on what is LCU. So LCU is measured by new connections, active connections, process bytes, rule evaluation. So it's not really that straightforward. And then you can go down and there is a pricing example. So this is the rule of thumb. Do not think that one solution is cheaper than the other. If your workload is spiky and then idle for a long time, API Gateway will probably come out cheaper. But if you are using consistently high volume, the pricing may differ, like ALB might be cheaper. But you gotta do that calculation. So don't assume that ALB will always be cheaper or API Gateway will always be cheaper. So as you can see, it's not a simple, straightforward ALB or API gateway decision. It will vary based on your use case. So depending on your project and application, check what features you need, go through the lists, do the price calculation based on the nature of the traffic of your application, and then decide. Alright, that's the video, guys and girls. I'll see you in the next lecture. Bye. Welcome, guys and girls, to this lecture. In this lecture, we are going to learn about vertical scaling versus horizontal scaling. This is a pretty important topic both for your system design interview as well as real-world system design. Alright, with that being said, let's jump into it. Let's say you have an application running in a server. We are also showing CPU utilization of the server. Currently, no traffic is hitting the server, so CPU utilization is around 0. Now let's say some traffic comes in, so CPU utilization goes up to 30%. Now more traffic starts to come in, also increasing the CPU utilization. Now the traffic keeps growing, increasing the CPU utilization to close to the max, so that this server cannot handle any more traffic. So if you have to scale this server, one option is to add more CPU or more RAM to this server, as in go to a bigger server. So if you move your application to a bigger server, it can handle more traffic. So this is what is called as vertical scaling, where you add more resources to your server, as in moving the app to a bigger server. So now let's do a vertical scaling deep dive. So going back to the previous state where your app was running in the smaller server and the CPU was almost near the max. So if we zoom out a little bit, how is the traffic coming to your server? So generally, you'll have an application load balancer in front of this server. To do vertical scaling, you have to bring up a bigger server. So let's say you spin up a bigger server and then you load your application. Next, you will cut over the traffic from the smaller server to the bigger server. And then you will delete the smaller server. There is a cutover window when you are moving from smaller server to the bigger server, and during this cutover period, your application might be down and unable to serve any user traffic. Another problem with vertical scaling is, so now you have this bigger server serving increased traffic. Now let's say traffic reduces. So now your application is still running in this bigger server. So the CPU utilization is low, but since you are running in this bigger server still, you will have to pay the price of the bigger server. You do not want to go back and forth from bigger server to the smaller server and smaller server to the bigger server. So summarizing vertical scaling challenges, the scaling up and down takes longer. There is a chance of missing transactions during the scaling cutover, and most importantly, there is a limit to the scaling. Servers only come up to certain CPUs and certain memory. You cannot keep on adding RAM and CPU to the server. So for massively scalable distributed system, vertical scaling is not ideal. Vertical scaling is also expensive. Now let's take a look at horizontal scaling. Going back to our regular application running in a server where the CPU is almost at the max, now if you have to scale up horizontally, instead of moving this application to a bigger server, you will simply spin up another server with your application running in it. And new traffic will start coming to this new server. So in horizontal scaling, instead of moving the server to a more powerful server, you simply add more servers. So diving deep into horizontal scaling, so in this case as well, your application in the server is fronted by, let's say, some sort of load balancer. And when the new server comes up, the load balancer simply starts sending traffic to this new server in the backend. There is no transition or cutoff period. So chance of missing transaction during scaling is very low. So what are some of the features of horizontal scaling? So it scales up and down faster, and the most importantly, horizontal scaling is massively scalable. So for all real-world distributed and scalable project, horizontal scaling is used. Horizontal scaling is also cost-effective because A, you do not need to keep on moving to more expensive and more powerful server. Instead, you are just spinning similar sized servers, and if the traffic goes down, you will simply kill the newly provisioned servers. One thing to keep in mind for horizontal scaling is legacy code needs to be refactored for horizontal scaling. If you try to scale your massive monolith with horizontal scaling, you end up paying more and it is not effective. Alright guys and girls, see you in the next lecture. Welcome guys and girls to this lecture. In this lecture, we are going to learn different types of scaling for different AWS services such as EC2, Lambda, and containers. So I covered the EC2 vertical scaling and horizontal scaling in the previous video, but just for consistency, I'm gonna cover that real quick here, then we are gonna jump to Lambda and container. Alright, so let's start with an application running on our tried and tested EC2. Let's say you have an application load balancer to this EC2, and this EC2 is running your application. This EC2 is of type T3.micro. So the traffic started increasing, and at a certain point, this EC2 reaches the max CPU. So for vertical scaling, you will provision a bigger EC2. Alright, so we spun up a M5, the 2x large, and your application is loaded to it. So at this point, the application load balancer will cut the traffic from the previous EC2 to this bigger new EC2. And once the traffic is switched, the previous EC2 will be terminated. So this is a vertical scaling. Because at the end of the day, you basically added more CPU and more memory to the EC2 rather than scaling horizontally. Alright, so now let's take a look at horizontal scaling. Okay, so in this case, application load balancer pointing to EC2, but instead of pointing directly to this specific EC2, the application load balancer will actually point to a auto scaling group. So we wrote ASG or auto scaling group. So as the traffic comes in to this EC2 and CPU reaches a specific threshold, another EC2 will be spun up in this auto scaling group. And that will be determined by the auto scaling group criteria, like at what percentage of CPU you need to scale, you want to scale, all that stuff. Okay, so another T3 micro came up with your application on it. Now load balancer will start spreading some traffic into this new EC2 as well. So note that in this case, you have multiple servers running, not just one, unlike the vertical scaling. So as more and more EC2s come up, the load balancer will start spreading the traffic across multiple EC2s. Now let's go to scaling of lambdas. So lambda can only scale horizontally, and lambda scaling is pretty straightforward. For each traffic, a new instance of your lambda spins up. So let's say you created this lambda function, and this lambda has 1 gigabyte of RAM. Now let's say this lambda gets invoked for the first time. So a traffic comes in, shown by this arrow. So then there will be a running version of the lambda you created. Now let's say the traffic increased. What will happen is simply it will create another lambda instance of your lambda, right? So as more traffic comes in, for each traffic connection, simply one instance of your lambda function will keep spinning up. And each lambda function will have 1 gigabyte of RAM allocated to it. And there is no auto-scaling group because each connection have its own lambda anyway, right? So there is no point of creating an auto-scaling group because it's always scaling when the traffic comes in, and as the traffic reduces, it will remove these additional instances of the lambda. Alright, so now that we understood how lambda scales, now take a look at how container scales. So let's talk about Kubernetes first. So for Kubernetes, your container is running inside a pod. Okay, so let's say we have this pod and we have this container, and at the end of the day, this pod is running in a EC2 worker node. So we're going to talk about Fargate as well, but let's just start with our vanilla, more commonly used way of running your Kubernetes using virtual machines. So let's say this is running within EC2. So what will happen is, so this pod will keep track of the CPU and resource utilization of this particular pod. And as traffic comes in, so this pod can handle multiple traffic connections. But with each traffic, the CPU and memory utilization of this pod will go up. And at certain point, using HPA or horizontal pod autoscaler, it will scale. Now the trick thing to remember is, during horizontal scaling of this container, it does not create another container in the same pod. The smallest unit of scaling for Kubernetes is this pod. So what it will do is, it will create another pod within that EC2 node with your container running, so this pod will start getting traffic. So you might ask, Raj, what happens if this EC2 is filled up? So yes, each EC2, depending on the family, like whether it's a T3 micro or M5.large, can only have certain number of pods, because as you put more pods in this same EC2, the CPU utilization of this EC2 is also going up. So at certain point, you have to scale this EC2 node. So we call it cluster autoscaler. So HPA is horizontal pod autoscaler. So with HPA, the number of pods increase within EC2, but with cluster autoscaler, the number of nodes increase. So at that point, I will add another EC2. Okay, so another EC2 got spun up. So now let's talk about Fargate. How does Fargate scale? So one thing to remember is, let's say you are running Fargate on Kubernetes, it has to run a pod, right? Because at the end of the day, the smallest running unit that you can manage and control is a pod. So for Fargate, the underlying EC2 you don't manage. So AWS manages where this pod is running. So it is more like a lambda. So let's say we are starting with one pod, and this pod is running as Fargate. So with Fargate, there is no underlying EC2. All you could see is this pod. So as this pod running in a Fargate takes more traffic, the CPU utilization goes up, and at a certain point, the Fargate scales. So how does a Fargate scale? It will just create another pod running the container for your application. So it is very similar to how the pods were scaling on the worker node, but in this case, you do not manage the worker node, right? So it's managed for you under the hood. And there is no cluster autoscaler in this case, because as more traffic keeps coming in, it will just create more and more pods. If under the hood, AWS needs to allocate more virtual machine or underlying infrastructure, they will. Alright guys and girls, that's how you scale EC2s, Lambda, and containers. Alright, see you in the next video. Alright, now that we understand horizontal and vertical scaling, let's go through a very common interview question. How can you make your application scalable for a big traffic day? So an average answer would look like put the virtual machines or EC2s in an auto-scaling group and use a load balancer. So nothing is wrong with this answer. Probably 3 years back, this would have been a great answer. But now cloud is mature, so any project you go and start working with, they already know about this. So when they come to you as a solutions architect, they expect something extra. So a good answer might be like, I will put my VMs or Amazon EC2s inside an auto-scaling group behind a load balancer, but in a big traffic day, such as Black Friday or Diwali, the burst will be too high. So if I let my load balancers to scale up naturally, it may not be able to keep up with the rate of rise up traffic. So to avoid that, I will pre-warm my load balancer before the big traffic event. Similarly, I will use scheduled scaling for my auto-scaling group. So all the necessary EC2s are up and running with the application on it. So when the traffic increases, they are ready to go. In case the EC2s do need to scale up naturally, I will make sure that the application machine image is as lightweight as possible. The more unnecessary libraries you put into your AMI, the longer it would take for the EC2s to spin up. If my application is connecting to a database, I will utilize a database proxy such as RDS proxy. In case of high traffic, sometimes applications will make rapid new connection to the database, and when the program stop querying the database for that particular instance, the connection will stay open. So when another traffic invocation comes, instead of reusing that lingering orphan connection, it will create another new connection. So this results in lot of orphan database connections taking up precious compute from your database. Using RDS proxy will eliminate that. RDS proxy will maintain the database connection full. It will reuse the orphan database connection. It will terminate as needed, etc. And on top of this, I will run IEM or infrastructure event management to ensure it can handle high traffic. So unless you have worked in a real-world cloud project, you won't know about this IEM. So IEM is an event that AWS runs before the big traffic day. So it will scale up the load balancer, EC2s, and then it will pass a high traffic to ensure that the application can handle it. Beyond this, you can also talk about breaking your applications into microservices, talk about advantages of microservices, that one specific API might need to scale up way more than another microservice in the same application. Using microservices, you can utilize that individual scaling of each APIs. Sometimes some candidate mentions that, oh, I will just migrate my application into Kubernetes or serverless, and then it will be handled these big traffic days. Which is not true, because Kubernetes serverless, they all have their scaling limits. So if you do mention that, okay, I want to go to Kubernetes or serverless, ensure that you study the scaling mechanism for those. But similarly, in serverless, you need to use provision concurrency, you need to increase limits for API gateway, etc. Similarly, for Kubernetes, study up HPA, cluster autoscaler, over provisioner, reducing the container image size, etc. Welcome guys and girls to this lecture. In this lecture, we are going to learn one of the most popular system design for interviews as well as real-world projects, 3-tier architecture. So in this lecture, we are going to learn the system design of 3-tier architecture, and then I'm going to go over some of the questions you can expect during your interview. And also, we'll take a look at how to achieve this three-tier architecture on AWS using regular virtual machines as well as serverless and containers. With that being said, let's get started. So first things first, why is this called three tiers? Because this architecture has three distinct layers or tiers. So the user accesses your application using a front end or presentation layer, and this presentation layer interacts with application layer or backend using APIs, and this application layer or the backend saves and retrieves information from the database as needed. These three distinct layers or tiers, presentation layer or front end, application layer or backend, and database, is the reason this architecture is called three tiers. Now let's focus on the presentation layer. So one example of presentation layer could be, let's say, Amazon.com website where you can browse different items, and this website could be running at Nginx or Apache web server. And there are multiple other options as well. But at the end of the day, this is a presentation layer where your users access your application. So let's say in the Amazon.com, the user liked one item and wants to add it to the cart. So as soon as the user clicks add to cart, so here you have to insert this information into a database, as well as you have to check some business logic such as where does the user live, whether the user is eligible to buy, credit card information, etc. So as soon as you click add to cart, the presentation layer calls the application layer or the backend where a bunch of business logic is running. So one example of this layer is your Java code running in a jar file, and this jar file is running in Apache Tomcat application server or Oracle WebLogic server. But you don't have to remember the Nginx, Apache, Oracle, etc. I'm just giving an example. At the end of the day, it could be any software where you can run this backend layer. If that's just an API running on container or running on Lambda, that's totally fine. Moving on to the database, you have many choices. Some of the popular ones includes Oracle, MySQL, PostgreSQL, but then beyond that you have your NoSQL database such as Cassandra, DynamoDB, etc. So going back to our three tiers on AWS, so one way to design this is you can run your web server on virtual machine or Amazon EC2. You can run the app server as well in Amazon EC2, and the app server can communicate with the database. And both of these EC2s will have some IP address. So your interviewer might ask you, how will the web server access app server, and how will the users access this web server from the internet? Because you must not hard code these IP addresses into your application. Because this EC2 can go down, you might need to scale, so it's not reliable to go by one IP address because that IP address can change. So you communicate between web server and app server by using load balancer. So the user can access this web server by using the DNS attached to this elastic load balancer, which is pointing to the web server. And in case of, let's say, any website, in our case, let's say Amazon.com, you can map Amazon.com to the DNS of this front-end elastic load balancer, which will point to the web server. And the web server will point to another application load balancer, and that application load balancer will point to the app server. So one of the most popular question could be, What are some of the single points of failure in this architecture? So the elastic load balancer are managed by the cloud provider and inherently highly available. So even though you see one icon of elastic load balancing, under the hood, this elastic load balancer is running in 3 different availability zones, so it is not a single point of failure. However, this web server and app server, which is running on single EC2s, is a single point of failure. And same thing is true for this database. So how will you make this architecture scalable and highly available? You do that by putting the EC2s for web server and app server under a auto scaling group, and you should have at least 2 web server and 2 app server EC2s in 2 different availability zones. In the auto scaling group, you can mention the minimum desired number of instances running, and that's where you can set how many minimum web server and app server you want to run. Now the interviewer might ask you about network security. How are you going to secure this kind of design from the network perspective? So you want to put as many components in the private subnet or green zone as possible. And only thing that should be on the yellow or red zone or public subnet is the elastic load balancer fronting the web server so that internet traffic can come to that load balancer. So the top load balancer you put on public subnet, and rest of the components you put on private subnet. You can also implement network security constructs for AWS, such as network access control list, security group on those EC2s to control traffic. You can also integrate AWS WAF or Web Application Firewall with Load Balancer that lets you monitor web requests and protect your web applications from malicious requests. You can use AWS WAF to block or allow requests based on conditions that you specify, such as IP addresses. You can also use AWS WAF pre-configured protections to block common attacks like SQL injection or cross-site scripting. Now let's turn our attention towards the database tier. So you can ask a lot of probing in this area. One area you can expect a lot of deep dive is whether you want to choose SQL versus NoSQL. So refer to that SQL versus NoSQL lecture on the talking points and how to answer that. And try to push the conversation towards AWS native databases, because AWS native databases offer out-of-the-box high availability, fault protection, and replication. If you run your database on EC2, you have to manage all that. So that's a rabbit hole you want to avoid in your interview. So let's say we are using Amazon Aurora for our 3-tier architecture. So you might get this question, how are you going to make this database highly available? That's the beauty of AWS native databases. Out of the box, Amazon Aurora is multi-AZ. So one copy of data is saved into multiple availability zones. And even if one availability zone goes down, Aurora will automatically promote another copy of the data as the primary instance. So this multi-AZ feature is within a single region. But if you want resiliency beyond a single region, you can use global database feature, which replicates your database into another region. Keep in mind, this 2 feature is true for DynamoDB as well, which is AWS's flagship NoSQL database. Another area you might get probed is database optimization. How do you handle high traffic? How can you optimize the database? Amazon Aurora provides a read replica, so you can use these read replicas to handle read traffic while the write traffic goes to the primary instance. You can also introduce caching layer using Amazon Elasticache. And you can also utilize caching in different layers of the architecture. So please refer to the caching lecture for details on this. And beyond that, there is always traditional query tuning for your application. Hey folks, Raj here. So this is the first 1 hour covering the basics from my full system design course. The full course is over 7 hours long. It covers topics from basics, intermediate to advanced. It comes with a certificate of completion, and it also has a 30-day money-back guarantee. If you are not satisfied, you get your money back, no questions asked. In the full course, we go over all the system design concepts needed to design your real-world applications, as well as answering system design interview questions. The course also has up-to-date quizzes to test your knowledge. After you master the system design concepts, we learn how to implement those concepts to create modern applications, such as 3-tier architecture on Kubernetes serverless EC2s, content-based messaging system, Tinder, Uber, Amazon, Fandango, IoT design, Shopify, TinyURL, WhatsApp, and more. This newly released course is currently bestseller in Udemy. I have included a $9.99 discount coupon in the description. Also, in the spirit of learning, I have created $9.99 discount coupon for all of my courses, so check them out in the description if interested. As always, thanks for watching this video. If you found this video helpful, please click subscribe, ask me any questions in the comment section, and share this channel with your friends and family. Alright, that's it for this one. I'll see you guys and girls in the next video.